molecule with permanent dipole moment will absorb microwave, and it must be in the gaseous state, because the gaseous state will be having the rotational freedom, and not in the liquid or solids. Molecule will lack that freedom, that is rotation. So in order to record microwave spectroscopy, microwave spectrum, we want to record microwave spectrum, the molecule must be in the gaseous state. So when I irradiate, molecule will absorb. During the interaction, there will be certain electric field of the microwave will be in the resonance with the electrical property of the molecule, which is your dipole moment. So there will be some interaction. Because of resonance, the energy from the microwave will be transferred to the molecule. So it will be the energy of the rotational energy is changed. It's like a change transition. So from so based on the selection rule, delta J is equal to plus or minus 1. So this is what on the other day we were discussing. So emission spectrum, all those things. So today, as I said earlier, we will do problems in microwave spectrum. So these are the things, as I said earlier, the energy levels, J is equal to 0. The first energy level is J is equal to 2B, 6B, 12B, 20B. All this I was mentioning. So only... so isotopic substitution, rigid rotator concept. So all this I was mentioning. So at room temperature. So these were the things. So we have discussed many things. Okay, we'll do some problems in rotational spectrum. Then we'll move to the vibrational spectroscopy. Okay, I'll take one problem, maybe a simple problem of, this is the problem. Just a recap what we have done in the previous class, and maybe that will be useful. So this is a simple problem. Let us so you are asked to calculate the B value rotational spectrum. So this is your B value of carbon monoxide molecule. So you are given the internuclear distance, which is 113 picometer, and reduced mass reduced mass. You know that, maybe I'll tell you the the molar mass. I will tell these are the things they have given. Molar mass of carbon the carbon is 0.012 kilogram per mole. Then oxygen they have given 0.016 kilogram per mole. So these are the things they have given, which is given in the problem. So these are the data for the problem. So you are asked to calculate what is the rotational constant. So how to proceed this problem? So reduced mass, which is for carbon monoxide, is mass of carbon, mass of oxygen multiplied, divided by mass of carbon plus mass of oxygen. And if you are given in molar mass, you have to divide the thing by 6.023 into 10 to the power 23 per mole. So how to do this problem, which is 0.12 gram per mole, and another is 0.016 gram per mole divided by 0.012 plus 0.016 kilogram per mole, of course multiplied by 6.023 into 10 to the power 23 per mole. So these are the things, and you know that this will get cancelled, and per mole will get cancelled. So finally, your answer would be this is what is your answer. So this would be around 0.00138 into 10 to the power minus 23 kilogram. So this is your reduced mass of carbon monoxide. And by knowing this, you know that you can find out the I value. I'll just add the papers. Okay. So I is equal to reduce mu carbon monoxide R square. So they are given, we know that it is reduced masses. Maybe this is 1, 2, 3. So 10 to the power 1.14 in 10 to the power minus 26 kilogram, and I have given the value which is picometer, that is 113 in 10 to the power minus 12 meter square. So if you solve this or if you work it out, this will be around 14.5 into 10 to the power minus 47 kilogram meter square. Okay, so by knowing these two I value, I can say what is my B. B is nothing but h square divided by 8 pi square I. This is B. In terms of joules, the unit will. So if you do this and substitute that, this will be 6.626 into 10 to the power minus 34 joule. For my convenience, I convert this into, for another joule, it is kilogram meter square second to the power minus 2 divided by 8, maybe 3.14 square. I know the I value, which is 114.5 in 10 to the power minus 47 kilogram meter square. So of course, this is your second. This is your second, and you have another second, second square. So this is one. This is joule into second. That is what I have converted. So since it is, I mean, not second. The second and this second will be second square. So this will be vanishing. So joule square, the joule square, joule, you know that the joule per second, joule second, and since it is square, I have taken like this. So this will be kilogram, this will get vanished, and these two. So your unit is in the joule. So if you calculate this, you will get the answer. It will be, so you will get the answer in terms of joule. I am not going to, please you solve it. So you solve this, it will be in the joules. So generally, this is what is the values in joules, and you can convert this in different form, different values. This is one problem normally they will ask you. And the other type is which I have given in the last class. By knowing the energy expression, one can calculate the different things. We'll do slightly the other problems in rotational spectrum. So by giving the values, so they're given one value, something. This is another rotational spectrum value. So they give the first line, first rotational line of, this is once again in pure rotational spectrum. The value is 3.8424 centimeter inverse. And you are asked to calculate the internuclear distance. What is the internuclear distance? And this is for, once again, carbon monoxide. This is only for, once again, for carbon monoxide. We'll take the same kilogram so that we can do this one. This is once again for carbon monoxide, 1216. Right. So how to do this one? By giving the first the rotation energy level, you know that. So this is your rotation energy. So E is equal to 0, E is equal to 1, E is equal to 2, and it goes. E is equal to 3, it goes. What is the value? Energy is equal to h square divided by 8 pi square j into j plus 1. Therefore, this will be 0, and this will be for j, if you substitute j1 and everything, this will be equal to b. So this will be equal to 2b. Then this will be, if it is 2, 2 plus 1, 3. So this will be 6b. And 12b, it goes. 20b, it goes. So they are given the first transition, first rotational transition. This is your first rotational transition. This is your second rotational transition. So first rotational transition, you know that it is 2b. The second rotational transition, it will be 4b. The third will be the 6b, etc. So not necessary that every time they will give you the problems will be the equally spaced consecutive rotation line. They will give you some values in second rotational transition. Second rotational transition, this is your second rotation. This is your first, this is your second, and this is your third, which means some molecules by undergoing, this is your selection rule, delta J is equal to plus or minus 1. Based on the selection rule, the molecule absorb microwave. Molecule in this molecule in the rotation level will move to the energy or the E1 state. Likewise, it goes. So suppose the molecule in this rotation level, if it absorb microwave, it will move to the second level. I mean the E2 state. Right. So that is what is the allowed state. So the transition. So what they are given is this one. So 2b they are given. And as I said earlier, not some problem, not always that the problems will be based on the energy gap. Rotational energy lines separation between the two consecutive rotation lines. Generally, you know that it will be 2b. So they may ask you the second rotation by giving the second rotation level, which is 4b, or the third rotation level, which is 6b. One must know that. Right, so it will be 2b. It's your first rotational transition. This 2b, which is equal to 3.8424 centimeter inverse. From there, you can calculate the b value, which is 1.92 into 10 to the power. Okay, centimeter inverse. In terms of centimeter inverse, it is just centimeter inverse. So by knowing b value, I can, as usual, I can calculate h square divided by 8 pi square I. So from this, I can be calculated. So substitute the same thing. So by knowing the b, so I will be equal to h square divided by 8 pi square b. So by this, if you substitute here, it is once again h2 6 into 10 to the power minus 34 joule second square, and this will be joule second square, and of course you have this 8 pi square I. So centimeters in the centimeter inverse. So this is the b is in the centimeter inverse, so that you can multiply this b with in order to make it the the other terms. So this is your b. B is in centimeter inverse. So substitute here, one can find out. So this is your b value. So you multiply by c, so that the centimeter inverse will get cancelled. So this is what is it? B in centimeter inverse, and c, that is 3 into 10 to the power 8, 10 centimeter per second. So this 2 will get cancelled, so that your value, now you have turned the b value in terms of b. Now if you calculate, this will be in terms of kilogram. You will get the value in kilogram meter square. Your I value will be 1.458 into 10 to the power minus 46. You just maybe I'll share this files. So this is your I value. By knowing the I value, by knowing the reduced mass of carbon monoxide, and R can be calculated. So R square. So R is equal to I mu C naught into 1 by 2. So this is 1.458 in 10 to the power minus 46 kilogram meter square divided by, I know the reduced mass which we have calculated in the last thing, 1.14 in 10 to the power minus 6 minus 26, 1.14 in 10 to the power minus 26 kilogram. So everything is in the root. So this kilogram meter. So since it is in the meter, so this will get cancelled. So my value will be in the meters. So attempted, it will be around 1.13 in 10 to the power minus 10 meter, which is nothing but 113 picometer. And just a reverse of this, I have given the R value earlier, and I calculated the other things. From now, by giving the first rotational excited, as I said earlier, I can give any excited state, provided the B value must be calculated from the excited state. So it is generally two types of problem: the spacing between the rotation energy levels and what is the rotation energy levels, as well as the gap, the energy gap between, the spacing between the rotation energy levels, and other thing is the giving the values. Right. The next problem would be once again, here is another problem. So I think I've given many the problems with regard to the population, etc. And so this is your problem with respect to this is another problem. So what are the energies of first rotation and the first energy? So this is for hydrogen molecule. Hydrogen molecule, they are given the internuclear distance for hydrogen molecule. This is around 74.1 picometer, the internuclear distance of the thing. And the first, you are asked to calculate what is the E naught energy level and E1 energy level, something like this. And what is the okay? I will. This is the data they have given. So the and hydrogen 1, they have given this is 1.0078 AMU, or atomic mass unit. So these are the data for hydrogen molecule. They are given some data. You are asked to calculate E naught of different energy levels, different rotation energy level. This is about your rotation energy level. And you may have a doubt that hydrogen being a homonuclear diatomic molecule, how can I relate with the rotation energy? Of course, rotation energy will not be the microwave will not give rotation energy. That doesn't mean that hydrogen it is not having rotation energy. It has rotation energy, or it is having rotation energy, but microwave inactive. The rotation energy of microwave, or the internuclear distance of microwave. This is the thing. You cannot calculate from the microwave spectroscopy, but it can be calculated using pure rotational Raman spectroscopy, which we will see later. So microwave will not give the answer, but it has rotation energy. The hydrogen has rotation energy levels, right? So rotation energy, but you cannot record by using microwave, right? Because since homonuclear diatomic molecules, they do not have permanent dipole moment, hence they are microwave inactive. But you can calculate internuclear distance of homonuclear diatomic molecules from pure rotational Raman spectroscopy, right? So probably from this data, these are the data that they have calculated using that Raman spectrum, pure rotational Raman spectrum. From there, they have taken this value, the internuclear distance, and how to calculate this problem. How to calculate the rotation energy levels of hydrogen thing. So these are the things they are given. So first thing is you have to calculate the reduced mass, because you need this reduced mass of hydrogen molecule. So which is M1 M2 divided by M1 plus M2. So M1 plus this is M1 hydrogen square, because this is your hydrogen. Both are hydrogen molecules, so you know that only same thing. So it is M1 square, and this is 2 H, right? So this will be so one of the H will be cancelled. So it is like half of the mass of the hydrogen. So H1, the reduced mass of hydrogen molecule will be equal to, so half of the thing, that is 1.0078 divided by 2. This will give you 0.5039 atomic mass unit. Some book they give us U, atomic mass unit. And remember, atomic mass unit, if you multiply by if you multiply this atomic mass unit, is 10 to the power one atomic mass unit is equal to 1.6605 in 10 to the power minus 27 kilogram. So if you multiply straight away, this will be 0.5039, and this is 1.6605 in 10 to the power minus 27 kilogram. Of course, this is uh, per mass unit. This is, so this thing will get cancelled, right? So this will give you the reduced mass of hydrogen molecule, which is equal to 8.37 into 10 to the power minus 28. You just attempt, probably, as I said, I will share this one, H2 molecule. So by knowing the reduced mass, I can calculate the internuclear distance, because I know I can calculate the internuclear distance. But in this case, they have given the internuclear distance, which is 74 picometer, 74.1 picometer 10 to the power minus 12 meter, and this is square, and reduced mass, which is 8.37 in 10 to the power minus 28 kilogram. If I do this, I can calculate the I value, which is, it will be, you try, it will be 10 to the power minus 48 kilogram meter square. This is your I value. So what is the meaning of the thing? I, moment of inertia, is nothing but the resistance offered during rotation for the resistance offered for a rotation. So from this, your EJ, so now you know what is the I value. So the main work is you are asked to calculate different energy levels of hydrogen molecule. So hydrogen molecule. So I just G is equal to J, and J is equal to 1, and I mean J is equal to 1. What is the J1, and E is equal to J, and you can go on. You can do for many things, but I'll just restrict myself. J is equal to 1. The formula is, you know, that this will be H square divided by 8 pi square I J into J plus 1. So if you do this, this will be 0. Of course, you know that. So this is H square divided by 8 pi square I J into J plus 1. So this will be equal to, if you try, so substitute your high value, J is equal to 1. So it is 2B. It is 2B. If you know B value, you can straight away do it. So for this one, it will be around 2.43 into 10 to the power minus 21 joule. Minus 21 joule. So this is your energy of hydrogen. And you may, what is there? You may compare with what are the thermal energy. The thermal energy, or how do their values compare with the thermal energy? So what is the thermal energy? Thermal energy. Thermal energy is equal to kBT. So when you make a comparison, So thermal energy, if you do this, thermal energy which is equal to, uh, if you do this for thermal energy, it is at room temperature. Room temperature, I take this as 298 Kelvin. So what is the thermal energy and this energy? I want to compare the J is equal to 1 and thermal energy of the system. So thermal energy, which is equal to 1.3, this is your Boltzmann constant, 1.38 in 10 to the power minus 23 joule per Kelvin, and this is 298 Kelvin. If you do this, this will be around 4.12 in 10 to the power minus 21 joule. Right? So this, look at these values, they are almost the same. Your thermal energy and the energy of the rotation, they are almost same. Rotation energy levels are almost same. And if you can extend this one, what is the by knowing the what you call as the angular momentum of, how can angular momentum of the thing, angular momentum, you know this. So this is your angular momentum. Any rotating body will have the angular momentum. This so when a body is moving in a straight line, it will have what you call as linear momentum, and for a circular path, when you linear momentum, which is your p is equal to mv. This is called as linear momentum. So this is your, but when you have a circular in your body which is rotating in a circular path, right? So this will have this velocity which is equal to v is equal to r. This is your angular momentum. Just to make a comparison, what will be the angular momentum if you walk? Suppose if you have some 60 kilogram weight, and if you are walking slowly, and probably your linear momentum will be when you have a slow walk, right? So if you need to happen, if you dash someone or if you hit someone when you are walking by mistake, and if you just say them sorry, and they will take it okay, right? But if you're running and running uh, in a straight thing, and if you try to if you hit someone, probably they will definitely will I mean, it will not be a easy conversation. So now the momentum will be changing because your velocity changes. Initially you are just walking, when you hit someone it is okay. The same thing, that is how you have to interpret. And maybe the linear momentum in it, why the train, the mass of train and the velocity of train, the collision the car, because its linear momentum is very high. When you hit something, it actually crushes because of the train, because it's the mass and velocity is very high. The moving speed is very high, right? The same thing when it is in a circular path, the body when it is revolving, then it is associated with the angular momentum. So angular momentum of the rotating thing can be calculated. So this is from this equation which I told you on the other day also, the E rotation, which is equal to L square divided by 2I. So by knowing the rotational the energy of the rotation, so this will be equal to 2EI, which is equal to L square. So therefore L will be equal to root of 2EI. Right? So I can calculate the rotation energy. By knowing the rotation energy, I can calculate the, so for what is the J1, so how speed, how fast it actually rotates, right? How fast it actually rotates. Likewise, I can angular velocity. What is the speed at which it's rotating? The speed at which it is rotating can be also calculated, provided So from this, I can calculate this is your E1. For E1, likewise your moment of inertia. If I know all this value, I can calculate what is my the angular momentum at j is equal to 1. Right? So if you do this, you can calculate it. It will be around, maybe you can try. And likewise, the angular velocity, which is equal to uh, multiple the product of moment of inertia and moment of inertia and angular velocity, which is equal to angular momentum. So from this equation, by knowing uh, the W, this is your angular velocity, which is equal to L by I. So by knowing the L, I can calculate the angular velocity. Angular velocity, the speed at which it is rotating. So the value will be, this will be around, so this unit will be around, this will be around kilogram meter square per second. This is the unit of angular momentum. Likewise, this is the unit of angular velocity, will be radians per second. So this is the unit of it. So all this, generally these are the things they will ask you, and I can calculate the other things also by giving the uh, by knowing the reduced mass. Say example, this is another problem. So calculate I. You are asked to calculate I of the I is your moment of inertia of molecule, HF molecule, and of course assume that they are given uh, the reduced mass, which is equal to 1.589 in 10 to the power sorry 1.9589 in 10 to the power uh, minus 27 kilogram, and R value, they have given these data, R value 92 picometer. Of course, it's not a big deal. So by using the formula, I can calculate the I value. So I value would be, which is 1.4 in 10 to the power minus 47 kilogram meter square. Right. Supposingly, if you are asked to calculate the B value, so this is one question, simple. Suppose if you are asked to calculate the B value, you know that, so H square divided by 8 pi square I. Right. So from this you can calculate, not since you know the I value, you can calculate it. Not doing it, it is 1.1 in 10 to the power minus 22 joule. So by knowing the B value, if you are asked to calculate the first excited or first rotational lines, first rotational um, line, or energy for first rotation line, the delta E for delta E of or I put it like this, rotation line, or your delta E of this transition J to 1 transition. So which is, you know that, which is your rotation line, which is 2B. So you will be knowing 2 into 10 to the power minus 22. So all these are different. So you are asked to calculate the energy gap. And what is the thermal energy? Your comparison of thermal energy for this process. Thermal energy, as the formula, you know that, which is kBT. And assume it is happening at 298 Kelvin. I mean room temperature, 298 Kelvin. So you must know that. So if you do this, this is 8.2 into 10 to the power. Or what they will ask you, what at the what temperature this is happening, this transition is happening. Provided they say that your delta E, so what temperature this is happening. This is your at what temperature? At what temperature? At what temperature? What thermal equivalence? What temperature you can undergo? At what temperature you can result in this transition? At what temperature this 2B transition can be this 2B transition 2B um, line can be achieved. Rotation line can be achieved. So this is another question. Maybe that is can be calculated from the thing. So kBt is equal to your this is your the energy required for the rotation energy gap. So this is 8.2 into 10 to the power minus 22 joules, right? So this is your so by doing your temperature can be calculated, which is 8.2 into 10 to the power minus 22 joule divided by kb. So kb, you know that, which is the Boltzmann constant. If you substitute that, you will find this is 1.3 into 10 to the power minus 23 into joule. For my convenience, I 1.2 into 20 to the power minus 23 joule per Kelvin. So joule will get cancelled. If you do this, approximately this will be 60 Kelvin. So same on irradiating microwave, I can undergo, I can perform the what do you call this? I'll get the first transition, which is 2B. The delta E is the energy gap is 8.2 in 10 to the power 22. The same thing can be achieved for this molecule, that is HF molecule at 60 degree. When I at 60 degree, probably at the same delta E will be of this much at 60 degree Kelvin, 60 Kelvin. Sorry, at 60 Kelvin you have. And what is the microwave wavelength? The wavelength. What is the wavelength of microwave which result in this transition? So lambda is equal to hc divided by delta E. This is another thing. So if you do this hc delta E, you know that value, which is this will be 2.4 into 10 to the power minus 4 meter. So this is very much between microwave and IR. So this is so this is the energy which when it is irradiated, the wavelength of the electromagnetic radiation when I irradiate it. So this can result in what you call as the transition, 8.2 transition, right? And likewise, you can the other the by giving the say example, you are given the uh, E1 value. E1 value is 7.6772 into 10 to the power minus 23 joule. So E1 value. You are asked to calculate what is your the first transition, the lambda required for first transition. That is delta E to EJ to E1 transition. So how to calculate this one? The lambda wavelength required for this transition. So this is your delta E from the formula is equal to Hc divided by delta E. Of course, E is equal to 0 for this one. So definitely your delta E will be also equal to the same value. So this will be around the H will be equal to the 6.626 into 10 to the power minus 34 joule second, and this will be around 3 into 10 to the power 8 meter per second. So this meter will get cancelled. So if you then you will have the energy value. So energy value will be 7.677 2 into 10 to the power minus 23 joule. So this joule and this joule will get cancelled. Remaining you have the meter. So that is the unit of the thing. And if you do this, so why I write this? Because your EJ, this is equal to 0. And the E1 will be equal to your delta E. So this difference is your delta E. And you don't have this value. So only this, that is why I have written like this. So the lambda will be around 2.59 into 10 to the power minus 23. So if you calculate the lambda, it will be around 10 to the power minus 3 meter and 2.59 meter. If you calculate, you will get like this. And this will be equal to, so this is what I have written. And for lambda for microwave will be As I said earlier, it is millimeter. That is 1 millimeter to 1 meter of wavelength. This is your microwave wavelength. Right. So these are the problems generally you will be asked, and I can go on ask doing many problems, and maybe the other is the last in my microwave spectrum. Supposingly, if you are given the rotational constant, a rotational constants of BHCl, hydrogen 1 Cl, which is 10.5909 centimeter inverse. And you are asked to calculate B2 Cl, this is 1. And if you are, sometimes you will be asked to HCl 37, this is 35. What is the rotational constant of it? You are given only the thing. So how to proceed this one? So the ratio, you must know the ratio of the B dash. B dash is your higher molecular weight molecule, prime, P prime. So this is H by 8 pi square IC and into 8 pi square I dash C divided by H. H square or H. This is in centimeter inverse. Since it is given in centimeter, this is your B value. So fine, this will give you my I dash divided by I, which is equal to B by B dash. And you know that I can relate this with my reduced mass, B dash, which is equal to I dash into I. And reduced mass is directly proportional to I. So your reduced mass of dash, this is what is it. Therefore, B by B dash will be equal to mu dash by nu. So this is by knowing this formula, I can solve this problem. So reduced mass prime is for higher isotope. So if I calculate for the hydrogen, if you assume that this is for, my question is, this is reduced mass of H2Cl35. This is mu HCl35. This is 1. And if you calculate it, in kilogram, this will be around 3.16. So I'm just giving the value 3.5. Maybe if you are given this value into 10 to the power 20 minus 27 kilogram. And for this 1.944 into 10 to the power minus 27 kilogram. If you do this, the ratio will be almost 1.4908. And my thing is, this is H1 Cl35 divided by B H2 Cl35, or I can very well write B DCl. So they have given the value of B1. This is what is that they have given, B1H. So from there, I can calculate. So B1H, which is 10 point. So this is your 10.59909 centimeter inverse divided by 1.94408, which is equal to B DCl. So this will be around 5.4478 centimeter inverse. So you can calculate by knowing the isotopes also. Likewise, if you know the BHCl, the other one, which is equal to divided by 35. The other one is BHCl37. So if you do this, probably the reduced mass value once again is a prime I mean H 37 Cl divided by mu H 35 Pl. Reduced mass. And by calculating, it will be around 1.629 in 10 to the power minus 27 kilogram divided by 1.626 in 10 to the power minus 27 kilogram. This will be around 1.00152. Right? So once again, by from this H135 Cl35, which is 10.5, this is b value of this one, divided by 10.9 divided by 1.00152. This is b value of HCl37 can be calculated. So which will be around 10.5747 into centimeter inverse. So these are the problems. These are the by isotopic substitution. From this, the B value can be calculated. I told you about the isotopic substitution. What is the isotopic substitution, etc. in the last class. Of course, rigid rotator, non-rigid rotator. I'll try to say the other one will be supposingly they have given for cyanide, they have given J is equal to 10, the maximum level, J max will be equal to 10 at 300 Kelvin. The same cyanide, J max is equal to 27 at what temperature? They are given. So you know the formula. J max is nothing but you are trying to find out which rotation lines will be highly populated. This is a formula. Kb T divided by 2 B HC root divided by 1 by 2. This is a formula for J max calculation. Which rotation level is highly populated at a given temperature for a molecule? For a given molecule, you have molecules and which rotation lines will be populated. And they have given this formula. They have found at 300 Kelvin for cyanide, it is 10th level will be more populated. More molecules will have that rotation energy level. At 27 degrees Celsius, what is the temperature for molecules have to occupy this level, 27 level? So you know that. So molecules are different. My molecules will have different rotation level. J is equal to 0, J is equal to 1, J is equal to 2, something like goes. And remember, the rotation vibration level of the molecule will be V0. Most of the molecule will have 0th vibration state. Right? So at what temperature this you can achieve this molecule will be having more molecules will have this rotation energy level. If you how to calculate this? How to calculate if you are given this type of problems? What is the rotation energy levels? You can okay. So this is okay. So this is the formula. By using this formula, by taking the ratio, it's the simplest formula. So this is your T at higher temperature or unknown temperature. This is 300 Kelvin temperature. It is higher temperature, temperature of unknown, higher temperature, and correspondingly the 27.5, which is 27. This is at 300 Kelvin. This will be around 10.5 or 10. Right? So if you do this, if you calculate this one from this equation, so this is the equation. The higher rotation level, maybe I call this higher rotation level. This is high, and this is higher population level. So this you know that. So knowing things will be at the bottom, and unknown things will be at the top. Maybe I put it like this. Right? So this is your higher rotation level. This is low temperature. This is your J max at the higher and J max at the lower. I put it like this. So this is a formula, general formula, 1 by 2. So substitute here and you will find the temperature will be around 25.8 Kelvin. So this temperature, when you use this temperature, when I heat this temperature, when the molecule acquires this temperature, most of the molecule will be occupying J is equal to 27 level. The rotation level of the molecule is at 27 degrees Celsius. I mean 27th rotation level, most of the molecule will be occupying. Right, just a few things, maybe how the rotational lines. So this is what I've so far discussed. There are many problems. I mean, there is no end to these problems when it comes to. So this is what is the microwave. I mean, the rotational spectrum. Rotational spectrum. Look at these lines. So this energy gap, this is for carbon monoxide. This is for carbon monoxide. Okay, so not all lines are equal. Some lines at maybe at the between. This line is more intense, and this is lower intense. Maybe the energy gap. This is your 2B. Maybe this is your 2B. The line which you can see. This is your 2B. So I just want to show you. Okay, so look at the isotopic substitution. The other peak, the small peak, this is probably I can show you. Can you see this thing? The point, the peak, small peak. That is your isotopic substitution. The larger peak is your larger peak correspond to C12. The smaller peak correspond to lower energy value. The lower energy values, which is C13, isotopic substitution. And this energy gap between these two energy gaps smaller, which will be 2B, and this energy gap will be 2B. This energy gap will be 2B. I put it like this. This energy gap will be 2B. Likewise, this energy gap is 2B. Smaller will be also 2B. And the smaller is for C13, O16. C13 and O16. And for larger, it is C12. This line is for C12, O16. Right? And they may are. And why this C13, O16 is only small? The intensity is very less. And why this is C12, O16 is intensity is greater? Probably that is due to the isotope C13 is the abundance, percentage of abundance of C13 is very, very less. Carbon 12 and carbon 14 is almost equal, 40, almost they make 98%. They are almost equal. But C13 is very, very less than 1% or 1%. That is the intensity because of the low abundance of C13O16. C13O16 probably it will be, when you compare C12 and C14O16, it will be very, very less. That is why the problem. That is why the reason why you get a less signal. I mean, the intensity is very, very. This intensity is very, very. This intensity I'm talking. This is very, very less. So this is why C13 is less. Probably C13 intensity is less because abundance is less, right? So this is how the. I mean, as I said, there are many problems you can go on discussing with regard to the rotational spectrum, and this is how the lines. If you look at the J value, J is equal to 0. The J is equal to 0 to 1 transition, you get one line. This I'm talking. So why the middle line is so intense? That is what is your J max, because your J max, as I said, the J max, this line, your J is equal to 16, 6, 7, and 8. They are highly populated. They are highly populated. And once again, the population also increases for at higher the population which is increase, the population increases, or population is more for j is equal to 6, etc. And this is very less populated, probably j is equal to 1, 2, 3 are less populated. So that you can calculate it from the j max value. And what all I so far said is for diatomic molecule. For diatomic molecule, this is what is your thing. But when it comes to the polyatomic molecule, they are classified based on moment of inertia. You have different types of molecules. Molecules are spherical top molecule, then your symmetric top, asymmetric top, linear molecules. It goes. Right, so they are broadly classified based on your moment of inertia. Molecules are for polyatomic molecule. Microwave spectrum of polyatomic molecule is based on the moment of inertia. The classification is based on moment of inertia, and based on which these type for polyatomic molecules you have different, not one the rotational constant, the b value will have two or three depending upon the for asymmetric molecule you will have three three rotational constants. You have ABC, they are designated as ABC. For symmetric top molecule, there are two types. Symmetric top molecule, they are prolate symmetry and oblate symmetry. And of course, you have the B value, you have two B values, which is like AB. For spherical top molecule, the molecules they do generally the moment of inertia will be on three axes. ABC represents on three axes. All the three will be same, and generally they are microwave inactive. So provided all the three are they sure not, I would not say microwave inactive. They will have only one moment of inertia. So for the only one moment of inertia, right? So I don't want to once again, probably if time permits, in the next class, I'll take up this for polyatomic molecule. Now I shall move to my next topic, the vibrational spectroscopy. Application-wise, as I said, the main application is in microwave spectroscopy. It's a simpler spectroscopy. Only thing is, it is mostly it is used to calculate what you call as your equilibrium internuclear distance. So coming to vibrational spectroscopy. So once again, vibrational spectroscopy is nothing but I'll start this vibrational spectroscopy. I'll straight away go with the simplest diatomic molecule. So diatomic molecule, it is like a spring. It is like a spring. It is the spring actually it is in the constant motion. It executes a constant motion, which I call it as vibration. They move to and fro motion. They have what you call as to and fro motion, which I call it as vibration. So it is displaced. It actually it elongates. When it is elongates, it is like the spring is like here. So it is elongated. The spring is like spring. The spring is elongated, and it is compressed. Sometimes it is compressed. So it comes to the original position, equilibrium internuclear distance. It is compressed, elongated. So it is like a simple the simple pendulum. So F is equal to minus kx. So it obeys Hooke's law. So Hooke's law. So it's like a simple pendulum. That is why the vibrating molecule. So vibrating molecule is actually, it is like a simple pendulum. So it obeys a single. So that is why it is called a simple harmonic oscillator. I approximate a diatomic molecule which is executing vibration as simple harmonic oscillator. And if I solve the simple harmonic oscillator, the the total energy of simple harmonic oscillator by solving the Schrodinger wave equation. So this is by the wave function, the solving the solving Schrodinger wave equation, where you come across Hermite polynomial, Hermite equation, right? So all this you come across. I'm the quantum mechanical. So finally, the simple harmonic oscillator uh, can be solved, and the equation is equal to h nu v plus half. And V is equal to the vibrational quantum number. It can have 1, 2, 3, etc. And remember, so this is what is the potential energy curve. If you draw the potential energy diagram, and the radius, the internuclear distance, so you get something like this, a potential well. So this is different vibrational energy level. V is equal to 0, which we have said. So V is equal to 0, V is equal to 1, V is equal to 2, V is equal to 3, V is equal to 4. It goes. So even at higher vibration energy level, the molecule is very much intact. Very much the molecule will survive even at higher vibration level. Higher vibration level. When I say higher vibration level, the executing motion will be more. It will be fast. Even that is what is saying, the molecule will vibrate very fastly. So this motion, to and fro motion, will be very fast. Vibrational motion will be very fast. So V is equal to 0. So this is your equilibrium internuclear distance. So this is by substituting the formula, this is h nu, half h nu. This will be 3 by 2 h nu, the second level. This is 5 by 2 h nu, the third level, and 7 by 2 h nu, the fourth level. It goes. Delta E, the difference between the two energy levels. This is a one quantum mechanical system. They are discrete. Energy levels are discrete. They are quantized. But you can see that some symmetry, they are equally spaced. This you cannot come across in any spectroscopy. In the rotational spectroscopy, J is equal to 0, J is equal to 1, which is 2B. This is 6B. And this is the energy gap is 4B. Energy gap is 2B. And the other energy, this is 6B. This 12B. This is for your rotation lines. But here, the delta E for any consecutive rotation line is h nu. This is symmetric in nature. That is an interesting part, right? So the rotation spectroscopy, the selection rule is delta V is equal to plus or minus 1. Simple harmonic oscillator behavior. This is the allowed transition. This is that is most of the molecule, as I said earlier, and this energy gap delta E, if it probably this will be around 5 electron volt. And if you look at the electromagnetic radiation, electromagnetic spectrum, which electromagnetic radiation has this energy, and this will be equal to your IR. That is why when I irradiate my IR, the molecule vibrating this energy level, V0 energy level, will now acquire what if molecule will have that, it will vibrate when it is in the V1 level. So it will vibrate fastly. And only a few molecules will be at this state. Only this few molecules will be at this state. And the other vibration level, only a few molecules. Most of the molecule in a system, most of the molecule will be at the 0th vibrational state. They will be at the 0th vibrational state. Right? The 0th vibrational state. Right? Of course, you can calculate that from the Maxwell-Boltzmann distribution formula. Let us maybe in the problems we'll do that. The little bit theory. So 0th vibrational state, this is your selection rule, and the delta E, that is V0 state to V1 state, will be the more intense state. More intense line, you get more intense spectral line for diatomic molecule. You get for this transition, more intense line. So if you call this line something like this, this is V2 V1 state, probably other states subsequently progressively it will intensity versus maybe the energy So this is your intensity. So this is more intense. The peak will be more height. The peak height will be high. This will be V1 to V0 state. V1 to V1 to V2, V2 to V3. Subsequently, are the progressively it declines. Intensity declines. Why? As I said earlier in the first class, intensity of any spectral line is directly proportional to the how much number of molecule which is undergoing that particular transition. And the probability also, it is also directly proportional to probability. Generally, probability is an allowed transition, forbidden transition. That is what is probability. And as I said earlier, zeroth vibration state is more molecule which is undergoing this transition. It is more molecule is absorbing IR energy. That results in what you call as a first signal, which is called as V0 to 1 transition, which is called as fundamental band. They are called as fundamental band in vibrational spectroscopy. So whatever you see in your if you get a more intense signal in IR spectrum, that is because of fundamental band. The fundamental band is more intense band. I'll take in another, I'll probably leave you by another 20 minutes. By 12:40, I will leave you. Right? So this is fundamental band. And the selection rule, as I said, the condition for molecule to be IR active, the molecule must have either permanent dipole moment or the molecule must acquire dipole moment during vibration. Two conditions, either permanent dipole moment or the molecule must acquire permanent dipole. During vibration, the molecule must have charge separation. During vibration, the molecule must have, during vibration, the molecule must, the molecule must, must acquire, dipole moment, charge separation. So this is a condition, right? For diatomic molecule, homonuclear diatomic molecule, H2, N2, all these molecules, they do not have permanent dipole moment. Even during vibration, they only undergoes what you call a stretching vibration. So they stretching vibration, and that too symmetric stretching. They undergo what you call a symmetric stretching. So for this symmetric stretching, still this does not produce dipole moment, so it is also zero. So therefore, the IR spectrum for you cannot record IR spectrum for pure IR spectrum. I'm talking pure IR spectrum. Only you get IR in the vibrational transition. You will not get the vibrational transition for H2 molecule. For a the heteronuclear diatomic molecule, so it has permanent dipole moment, and during vibration, it also produce the thing. So therefore, by using this, the dipole moment is equal to this condition, dou alpha mu divided by dou r into q. This comes from Maclaurin series of applying for dipole moment of the molecule. You get a series, higher powers of the Maclaurin series are actually ignored. We only take this thing. Apply this for the transition v dash to v double dash. Of course, maybe for more, which I said higher level is the 1 dash, which is integral v dash to v double dash to v dash. So psi v dash operator psi v double dash d tau. If it is allowed transition, this is your operator. So this is your operator psi v dash operator is nothing but your mu naught plus dou mu divided by dou r into q psi v double dash d tau. And this triple product, this is a triple product which you come across in group theory. This must belong to a totally symmetric irreducible representation. If that is a condition for any molecule, the P1, PV double P say this is V dash, right? V dash to V double dash. V dash to V double dash will be this integral will give you a non-zero value which will be allowed transition. So for heteronuclear diatomic molecule, this entire thing will not be equal to zero. But for homonuclear diatomic molecule, the operator will be equal to zero. So everything will vanish. Right. So this is the condition for the simple harmonic oscillator. And remember, the molecule, as I said earlier, the diagram, the homonuclear diatomic molecule. So the molecule will have, this is your 0-point energy, the 0-point energy, that is lowermost energy, which is equal to E is equal to half h nu. That is your 0-point energy. The molecule will execute vibration even at 0 Kelvin. The molecule will execute vibration even at 0 Kelvin. So there will be vibration. Right? So that is the mechanical prediction. This is what is it. And remember, the rotation energy level, which between any vibration level, as I said, I can accommodate many rotation energy level. Between V0 and V1, I can have many rotation energy level. This is J is equal to 1, J is equal to 0, J is equal to 2, it goes. J is equal to 3, it goes. So this is what your IR is all about. Between V0 to V1 is a fundamental band, V1 to V0, V1 to V2, subsequent lines. That is by maintaining the selection rule, delta V is equal to plus or minus 1. And this is your microwave. This is your microwave or pure rotational spectrum. By selection rule, delta J is equal to plus or minus 1. Therefore, when I irradiate when I irradiate IR, it also affect the rotational part of the molecule. It also affect the rotational part of the molecule. So therefore, your energy transition is combination of vibrational as well as the rotational. So when I irradiate IR radiation on the molecule, vibration energy alone does not, the vibration energy alone is not changing. It also undergoes the rotational change. So I just show you a simple, this is V0, V1 state. I'm taking only two states, vibration, still that nothing is happening to the electron. So I'm just focusing my two vibration energy, and I said I can accommodate different rotation energy for the molecule. So this is J is equal to 0, J is equal to 1, J is equal to 2, J is equal to 3, it goes. This vibration energy level also I can have different rotation. This is J is equal to 0, J is equal to 1, J is equal to 2, J is equal to 3, etc. It goes. Likewise, I can have rotation energy level, vibration for every, this is how. Supposingly, if I irradiate IR radiation, and this is my vibration transition. This is my vibration transition. So vibration transition, V1 to V0. So my delta V is equal to 1. So as for the selection rule, it is vibration transition. And remember, it is also undergoing rotational transition. This is also undergoing rotational transition. I just show you by red line. This is also undergoing a rotational transition. That is delta J is equal to 0 to 0 transition. And supposingly, if this is your rotational transition, the vibration transition, a molecule which undergoes vibration transition. So vibration transition for this one. Maybe for my convenience, I took this line 2. This is 1. This is correspond to 1. Line 2 is, look at the delta V. This is V1 to V0 transition. So it is a vibrational transition, plus 1 allowed transition, fundamental band. And look at the rotation energy level. During the process, J is equal to 1, final state. J is equal to 0 at the initial state. my delta J is equal to +1. Likewise, if I start here and stop here, say, assume I stop here. This is my third line, where line 3, where delta V is equal to delta V minus 1, which is equal to 1. My delta J is equal to, it starts from 1, I mean, starts from 1 and stops at 0. Third one is stops at 0. Look at this one. Stops at 0. J is equal to 0. So, as for my difference, this will be minus 1. So, these are all what you call as pure the rotational vibration spectrum. Rotational vibrational vibrational spectroscopy. That is rotation lines in vibrational spectra. Rotation lines in vibrational spectra. And this is what is what is called as the thing. What is called as the PQR branches, formation of PQR branches. And the first line, which they were J is equal to delta J is equal to 0. The other thing, this is your something like this. You get a, this is your IR signal, and you inside you get different lines. This is your the line gap is equal to 2b. Once again, the rotation line is 2b. So this is your R branch. By maintaining the selection rule, delta J is equal to +1, and delta V is equal to this. You get because of delta V is equal to +1. Inside you get rotation lines, and likewise here also you get some rotation lines, and the energy gap will be, once again, it will be 2b, and this is based on the selection rule. Delta J is equal to -1. So PQR band formation in vibrational spectrum, vibrational rotation spectrum. Right, and remember, I have approximated my molecule as a simple harmonic oscillator. So therefore, I am just showing that molecule can have, this is your vibrating molecule, J is equal to 1, J is, and even at a higher vibration energy level, molecules survive according to simple harmonic oscillator. But in reality, molecule when it vibrates very fastly, molecule will break into atoms. So that is not considered by simple harmonic approximation. So according to simple harmonic approximation, the molecule can vibrate at any vibration energy level. They can have any vibration energy level, any vibration energy, which means it can vibrate at any speed of vibration. Still, the molecule can survive according to simple harmonic oscillator approximation. But in reality, molecule at certain point, when it vibrates very fastly, it will break. It will break. Right? So that is one assumption that we need to change. You need to have, that is what I call as unharmonical behavior. Unharmonical behavior. So energy of unharmonic oscillator. So that is the thing. And that is another thing. And you know that by the fundamental band, which is the V0 to V1 transition, can be given in terms of frequency, that is H delta E, the fundamental band, which can result your delta E. So which is equal to 1 by 2 pi root K divided by mu. I take my molecule as a reduced mass. So this is your fundamental band. And if I give this in terms of frequency, this is my 2 pi mu K by mu. This is in terms of per second frequency. Suppose if I give it in terms of fundamental band, in terms of centimeter inverse, I have to divide by 2 pi C into root K by C. So I can calculate, by knowing the fundamental band, I can calculate this particular parameter of the molecule, which is the force constant. So force constant, take the square of, take this one, 2 pi C mu bar, which is equal to K by mu root, taking the square, this will be equal to 4 pi square C square mu bar square. This will be equal to K by mu. So taking the K on one side, which is a force constant, and force constant is, which is nothing but 4 pi square c square, velocity of light, the fundamental band in centimeter inverse, the reduced mass of the molecule. I can calculate the force constant. Force constant. So this is your pendulum. If your comparison, so if this is a molecule, something like this. So this is a force constant. The displacement. So this is for your maybe the double single bond carbon. This is for your double bond carbon. This is your triple bond carbon. So what does it implies? Assume that the displacement. This is your displacement. So if the molecule is displaced so wide, the K value is less. That means when the molecule has K value is less, probably it will be wider. Or in terms of the same molecule, I put it like this. The same molecule, if I have this value, something like this. So this K1, K2, K3. So which value is high? My K3 is high. What does it mean? So it is given in Newton per meter. So I have to spend more amount of energy to displace the molecule. So C triple bond C, the K value of C triple bond C will be very high. That means in order to disturb the in order to disturb the vibrating molecule, I have to give more energy, more force. Then only the molecule will be displaced. That the molecule will be stretched. Your C double bond C will be, which is greater, C double bond C will be greater than C single bond. So among the three, triple bond C will have more K value. So by knowing this formula, by knowing the fundamental value, I can calculate the force constant. I'll just show you one. What is the rotational spectrum is all about? I'll just show you in another 5 minutes, and I'll just leave you. We'll continue the problem. So this particular software, which actually gives you the rotational spectrum. So example, what is rotational spectrum? All this is given by this one. So these are the different rotation lines. And as I said, first line is 0. They are quantized. Look at this video. Look at the screen. Maybe I think it is visible if I believe 2b, 6b, 12b, etc. Right? So your b is equal to h by 8 pi square I j into j plus 1. So they are quantized, but they are not, the delta is not constant. If I take the HCl, this is my HCl. Right? Look at this when it is in the different energy level. Look at this, how fast it rotates. At 20B, it is rotating fastly. It's rotating fastly. Maybe at 2B or 6B, look at the rotation. It is slow. So when the molecule is excited, if a molecule at rotating energy, if it is at the 2B, if absorbs microwave, it goes to 6B. At 2B, it will have different rotation. At 6B, it will rotate differently. And at 20B, it rotates differently. So from 12B, the molecule at 12B molecule. So not that all molecules. So certain molecules, if you have 100 molecules, some may have 2B, some may have 6B energy, some may have 20B energy. So the 20B energy, when it absorbs molecule, it moves to the next rotation level, it will be 30B. Right? So for water molecule, maybe I'll show you for water molecule. This is polyatomic molecule. So and remember the energy levels are same, and this is how it rotates. This is how it rotates. Of course, it have different B value. This is I'm just giving for water molecule. I said it has 3 B values, polyatomic molecule. So it rotates fastly when it is at this axis. Maybe at if I call this as at Z axis, which is this direction. This is my Z axis. So I keep this rotational axis and rotating. So this is what I can rotate another 3 axes also, X axis and Y axis. Right. So for carbon dioxide, the rotation energy level, this is how it rotates. Right. But remember, carbon dioxide does not have dipole moment. Okay. Coming to vibrational spectroscopy, I just show you vibrational spectroscopy as what is the vibrational spectroscopy is all about. Once again, I take, so this is what I said, the internuclear distance, potential energy curve, simple harmonic oscillator, the energy levels. So as I said, even at higher vibration level, the molecule will be very much safe according to simple harmonic oscillator, but it is not true. Molecule will break at certain point. That is called as dissociation energy. So every molecule will break when it is at higher vibration energy. And this is by approximate the molecule as anharmonic oscillator by giving the potential energy diagram, what you call as a Morse diagram, Morse potential energy curve that can be explained. So I will stop here. Maybe I'll come to the example point of view. If any example, this is as I said earlier, it obeys Hooke's law, the simple harmonic oscillator, all this I said, the fundamental band, I told you, but I have not started the example of rotational spectrum, maybe for water or HCl, I'll show you. No, it is not. Right. This is my vibration. Look at the vibration. So it can have only one vibration. So as I said, most of this population is V. Most of the molecule, if I have 100 molecule, most of them belongs to V0 state. That gives you the fundamental band. The other transition, V1 to V2 transition, because V1 transition is less populated, maybe the intensity will be less. It is progressively, the probability is progressively decreasing. And I'll give you the based on so if you look at that, how many number of modes, the molecules, it will have only one vibrational modes. So it is a linear molecule, 3n minus 5. So two atoms, 3 into 2, 5. So one vibrational mode. So it will have only one vibration. All the molecules will have only one vibration. So coming to the other example, maybe the water, carbon dioxide. Look at the carbon dioxide. Technically, carbon dioxide. I don't know why it is not coming. Okay, carbon dioxide. The number of vibration modes, 3n minus the number of, it's a linear molecule. So 3n minus 6. So number of modes is 3n minus 5. 3n minus 5. It's not a linear molecule like your earlier case. So 4 vibrations. Look at, we don't know whether we can see that 4 vibrations. So this is one vibration. So it's symmetric stretching. This is symmetric stretching. This is your symmetric stretching. Suppose if the molecule is at so look at that V1 state. V1 state, now it is vibrating fastly. Now V3 state, the molecular vibration is so fast. Vibration is so fast. Right? So this is what is that you have to remember. This is what you have to remember. Right? Now it is, so V1 state, the 0 point energy, Now it is slowly vibrating. This is a what do you call as bending vibration. It is bending vibration. So it has two bending vibration, one symmetric stretching and asymmetric stretching. One asymmetric stretching. Your symmetric stretching, no dipole moment, so that is IR inactive. Asymmetric stretching IR active, and for two vibration modes, two bending modes, it will give same frequency, degenerate frequency. So for carbon dioxide, you get two IR signals, two fundamental bands. And finally, water. I'll just show you water. You get for water you get three signals. We'll see the three. So this is your water. So this is your bending. So you have this is bending. It's only bending shows. So three possible. Non-linear molecule 3n-6, three atoms. So 9, 3 into 3 9 minus 6. So three modes of vibration. So if you have three possible, if you have a assembly of molecule, some molecules will have possibly the vibration, asymmetric stretching, symmetric stretching, and bending. So you get three IR fundamental band. Look at this when it is at the low, V is equal to 1, how fast it is vibrating. V is equal to 2, how fast it is vibrating. So look at that, different vibrational signals. For water molecule, different vibe. So when V is equal to 3, the vibration mode still increases. So when vibrating molecule, when I irradiate with IR, suppose a molecule is vibrating at V3, takes up the IR, it will go to V is equal to 4 state, right? V is equal to 4 state. And I'm just showing only one signal, that only one type of vibration. And it is also having the other vibration, other two vibration. Maybe I'll select this one. Maybe one state, the higher energy. This is your asymmetric stitching. Look at this one, asymmetric stitching. So which requires, asymmetric stitching requires more energy than your symmetric stitching. This is your symmetric stitching. Both are stretched the same way. Symmetric stitching. Symmetric stitching at V is equal to 1. Symmetric stretching at V is equal to 0, it will be slow. So three types of, for an assembly of molecule, some molecules will stretch at asymmetric stretching, some may have. So which will require more energy? Asymmetric stretching will require more energy. Right, I'll stop here. I'll complete the calculation. I'll do that calculation in the next class.